Hello everyone, in this video we will cover the section 14.8. In this section we learn Lagrange multipliers method for maximizing or minimizing a general function f of x, y, z or functions of two variables stated as f of x, y subject to a constraint of the form g of x, y, z is equal to k, or g of xy is equal to k for functions of two variables. So in this section our aim is to find the maximum and minimum value of a function of three variables or two variables such that all the points satisfy the condition written here. For functions of three variables, the condition is a surface given here, g of xyz is equal to k, which represents a surface in three-dimensional coordinate system, or the condition is a level curve for functions of two variables. So at which point satisfying these condition do we have a maximum or minimum value for a function of three variables or two variables? Our aim is to find the maximum and minimum value such that we look for this value for all the points satisfying the condition. We have a constraint for the points. In this case, what should we do to find the maximum or minimum values for a function? So for this we have a method which is called the Lagrange's method. So to find the maximum and minimum values of f, x, y, z subject to the constraint, we have a condition for the points g of x, y, z is equal to k, or instead of g of x, y, z or f of x, y, z, you can consider the functions of two variables, or you can consider any multivariable functions for this method. Assuming that these extreme values exist and the gradient of g, which is a vector function, which is obtained by finding the partial derivatives, if you remember, is not equal to the zero vector on the surface g of x, y, z is equal to k. When we consider all the points satisfying this equality, so the values of the vector function the values of the gradient vector of the function g should not be equal to the zero vector. So we have two steps for this method. We will find all values of x, y, z and lambda such that these are satisfying these equalities. Actually, we have for functions of three variables, we have four equations here. Four equations in the variables x, y, z and lambda. For functions of two variables, of course, we will have three equations in the variables x, y and lambda. Okay, therefore we find all the values of x, y, z and lambda by using these equations. We have four equations, and then we will evaluate f at all the points that result from the previous step. So the largest of these values is the maximum value of f, and the smallest is the minimum value of the function f. Just we will find the gradient vectors and we will form an equation for the gradient vectors written here, and then we use the constraint, the condition given at the beginning, and then we solve these equations for the variables x, y, z and lambda, and after finding these values, we will evaluate the function f at these points obtained from the step 1, and the largest value will be the maximum value of f among them, and the smallest will be the minimum value. And the number lambda is called a Lagrange multiplier. Okay, this is the method for finding maximum and minimum values of f subject to the constraint g of xyz is equal to key, or g of xy is equal to key for functions of two variables f of xy. For example, find the extreme values of the function f of xy, which is a polynomial, you see, x squared plus 2y squared, on the circle x squared plus y squared is equal to 1. At which point on the circle x squared plus y squared is equal to 1 gives, at which point do we have a maximum value for f defined in the example on the unit circle, or at which point do we have a minimum value for f on the units on the circle whose radius is equal to 1. Namely, we have infinitely many points on the circle x squared plus y squared is equal to 1, and polynomials are defined everywhere for functions of two variables also. Therefore, we can consider any point in the xy coordinate system, in a two-dimensional coordinate system. Any point will be in the domain of f, but we look for maximum and minimum values of the function f on the circle, at which point can be this point, can be this one, can be this one. So at which point we can we find the maximum, the biggest value of f. What is the biggest value of f for all the points on the unit circle? This is the problem for this example. So for this, we will benefit from the method which is called the Lagrange Multipliers method. So we know the constraint g of xy is the circle. This is the constraint because all the points should satisfy the equation of the circle, because we want to find the extreme values of the function on the circle. That means the constraint, the condition for this example is the equation of the circle. Therefore, g of xy should be the equation of the circle x squared plus y squared, so it is equal to 1. Instead of k, we have the number 1 because we want to find the biggest and lowest value of f on this circle. So using Lagrange multipliers, we solve the equations gradient f is equal to lambda times gradient g, and g of xy is equal to 1, which can be written as, gradient f, this is a function of two variables, so we have two components for the gradient f, which can be written as fx, which is the first component, and this is the partial derivative of f with respect to x, and fy, which is the second component, and this is the partial derivative of f with respect to y, first partial derivative. From here easily we can find the partial derivatives, and also we should find the partial derivative of g to get the equality written here. So from here, since we have the vector equality, the first components has to be equal to each other, and the second components has to be equal to each other. Okay. So fx is equal to lambda times g of x from this equation, and fy is equal to lambda times g of y, and we have the constraint. You see we have three equations in the variables x, y, and lambda. Since we have functions of two variables, we have two independent variables, and we have the Lagrange multipliers, which is lambda. And from the first one we obtain what is the partial derivative of f with respect to x. This is equal to 2 times x. We consider the variable y as a constant. Therefore, the partial derivative of f is equal to 2 times x. Lambda times the partial derivative of g with respect to x, it is again 2 times x. And we have the Lagrange multipliers obtained from the formula written here. And similarly, you can find the second one, which will be written as 4y is equal to 2y times lambda. And the last one is already given in the example, which is the equation of the circle. So you see we have three equations for the variables x, y, and lambda. So from here we will find the values of x and y to get maximum and minimum values of the function defined here. According to the Lagrange Multipliers method, to continue the second step, we should complete the first step. In the first step, our aim is to find the points satisfying these equations. So we have from 9, we have two possibilities for the values of x and lambda. From the first one, you can find easily. So if we write 0 for x, we get the equality. This is the first possibility to get the equality. And the second, if we remove 2x in every side of this equality, so we have 1 is equal to lambda. This is the second possibility. If we write 1 for lambda, we get the equality. And if we write 0, we get the equality for the first one. Okay. And then we will consider these possibilities separately. So if we say x is equal to 0, the first possibility, if x is equal to 0, so what can we say? We don't have x for the second one, so we will use the third one to get the value of y. So if we write 0 for x, we get y squared is equal to 1. Therefore, from this possibility, we obtain y can be plus or minus 1 from the first possibility. And from the second possibility, namely lambda is equal to 1, if lambda is equal to 1, so we have 4y is equal to 2y, and from here we use the second one now for this possibility. So 2y is equal to y actually, and if we remove y, so we get 2 is equal to 1, which is not possible. This is impossible situation. So we have the only possibility to get the equality. Y should be equal to, y has to be equal to 0 from the second one. Therefore we write y is equal to 0 for the second possibility. So from the first possibility we have two options. The point can be 0, 1, or can be 0, minus 1. Okay. From the second possibility we obtain y is equal to 0, and using the third one, again we have x squared is equal to 1, so x can be plus or minus 1 from the third one, which is the constraint. So from the second possibility, again we have two options for the point. So the first component can be 1, the second component is 0, or the first component can be minus 1 and the second component is 0. So we have four possible points satisfying these equalities. Okay, this is the step 1 for the method in this section, for the example given here. So therefore f has possible extreme values at the points 0 to 1, 0 to minus 1, which are the points obtained from the first possibility, or 1, 0 and minus 1, 0 is obtained from the second possibility. So evaluating f at these 4 points, we find that 2 for the first one, 2 for the second one, 1 for the third one, and 1 for the last one, using the definition written here. Just we write the numbers for x and y from here in the definition of f, and we obtain the values of f. So what is the biggest value? So the biggest value is 2. We have the same result for the points written here, and the minimum value is 1. That's it. The biggest value of the function f is equal to 2 on the circle, and it takes this value at the point 0 to 1 and 0 to minus 1. 0 to 1 at this point and 0 to minus 1 at this point. At these points we have the biggest value for the function f, and also at these points on the x-axis 1 0 and minus 1 0 we have the minimum value of the function defined here, okay, which is equal to 1. So all values of f on the unit circle should be between 1 and 2. 1 and 2. Okay, this is an important information for the function according to the condition. Another example, actually you know this example from the section 14.7. So we have a rectangular box without a lid. It is to be made from 12 meters square of cardboard. Find the maximum volume of such a box. Okay. So the top side of the box is empty, and as the section 14.7, we let x, y, and z be the length, width, and height, respectively, of the box in meters. You see. So the volume will be the multiplication of them, x times y times z, and we want to maximize this function. Actually this is a function of 3 variables subject to the constraint. So the rectangular box is to be made from 12 meters square of cardboard. That means the surface area of this box except the top side should be equal to 12 meters square. Okay, what is the surface area of this rectangular box except the top side? So when we consider front and back side of this box, so we write y times z, 2 times y times z, and right and left side will be equal to 2 times x times z, and the bottom side is x times y for the area, x times y. So this is equal to 12. So using the method of Lagrange multipliers, we look for values of x, y, z, and lambda such that, so this is the constraint, you can see this is the constraint, because we want to find the maximum value of this function, which is the volume, such that the surface area is equal to 12. Okay, we have an equation in the variables x, y, z. Therefore this will be the constraint of this function, because what is the maximum value of this function such that all the points satisfy this equation. This is the condition, this is the constraint of this problem. Therefore we write g of x, y, z as the surface area of this rectangular box without a lid, and the function is the volume of the rectangular box for the example. So we can use the Lagrange multipliers because we have a constraint for the problem. In this case we will use the Lagrange multipliers, or directly you can use the second derivatives test, like the section 14.7, if you remember. Using the method of Lagrange multipliers, we look for values of x, y, z, and lambda such that the gradient of the volume is equal to lambda times the gradient of g according to the method, and this is the constraint. So this gives the equations. So we should have 4 equations. You can see from the vector equality we can find the equalities written here. This first one is obtained from the first components, the second one is obtained from the second components of the gradient vectors, and the third one is obtained from the third components of the gradient vectors, and the last one will be the constraint of the problem. So we need to find the partial derivatives of the functions written here. What is the partial derivative of volume with respect to x, which means the variables y and z are constant in this case. So we have actually 2 times x. 2 is corresponding to the y times z. Therefore, its derivative will be y times z with respect to x. So we write this here. It is equal to lambda times the partial derivative of g with respect to x. From here, easily you can find it is equal to 2 times z plus y. The second one is corresponding to 0 since y and z are constants in this case. And you can see the partial derivative of g with respect to x. And similarly, you can find the others. And we have the constraints. So from here we should find the values of x, y and z, also lambda. We have 4 unknowns, but we have 4 equations in the variables x, y and z, x, y, z and lambda. So there are no general rules for solving systems of equations. Sometimes some ingenuity is required to solve these equations to find the values of x, y, z and lambda. So in the present example here, you might notice that if we multiply the first one by x, so we obtain x times y times z on the left hand side. And to get the same term for the second one, we multiply this by y. So we have x times y times z for the second one. And we multiply the third one by z to get x, y, z for the left hand side of the equality. So we multiply by x, we multiply by y, and we multiply by z. So from here we have x, y, z is equal to, if we multiply by x, the right hand side, so we have 2xz plus xy, and similarly if we multiply the second one by y, we get 2yz plus xy, and for the third one we have 2xz plus 2yz multiplying by z, and the left hand sides are equal to the same term x, y, z. Therefore, we observe that lambda is not equal to 0, because if lambda is equal to 0, it would imply yz and xz and xy is equal to 0 from here, which means the size of the rectangular box are equal to 0, which means the volume is equal to 0, which is not possible because the surface area is 12. Therefore, we cannot obtain 0 for the sides of the length, width and height of the rectangular box. Therefore, lambda is not equal to 0. So since lambda is not equal to 0 for these equations, and we have the same terms for the left hand side of these equations, it means that 2xz plus xy is equal to 2yz plus xy. Also, 3 of them are equal to each other. Okay, so by using the first 2 terms, we obtain 2xz plus xy is equal to 2yz plus xy, which gives, from here by removing xy's, xz is equal to yz. And we know z is not equal to 0. The height cannot be 0 for the rectangular box for the example, because the surface area is equal to 12 meters square. And also the volume will be 0 if the height is equal to 0. Therefore, we write z is not equal to 0. Therefore, we can remove z's here. So we have x is equal to y. And from the second and third one, we have 2yz plus xy is equal to 2xz plus 2yz. So from here we have, by removing 2yz's, xy is equal to 2xz and x is not equal to 0 to get volume which is not equal to 0. So from here we obtain, by removing x in each side, y is equal to 2z, and from the previous one we know x is equal to y, so as a result we obtain x is equal to y is equal to 2z. So if we put them in the constraint written here, for x and y we write 2z. So if we write 2z, from here we have 4z square. For the second one we have 4z square. For the third one we have again 4z square, which is equal to 12. And from here we have 12z square is equal to 12. So from here z square is equal to 1. And the height cannot be negative, therefore z is equal to 1. And from here we can write x is equal to 2, y is equal to 2. So we can find the maximum volume of such a box as 4, which is the multiplication of the width, length and height. Okay, so this agrees with our answer in the section 14.7. Please look at the lecture note of the section 14.7, and the maximum volume will be 4. Another example, find the points on the sphere x squared plus y squared plus z squared is equal to 4 that are closest to and farthest from the point 3, 1, minus 1. So our aim is to find a point on the surface, you see, such that the distance between this point on the surface and the given point in the example will be the smallest value for all the points on the sphere. And also we will find another point such that the distance between the point on the surface that we want to find and the point given in the example will be the biggest value for all the points on the sphere. What is the closest point such that the distance will be smallest one, and what is the point on the sphere such that the distance between them will be the biggest one. Okay, so geometrically you can see our function will be the distance, because we want to maximize or minimize the distance between the points. Therefore we form the function by using the distance formula, generally from a point on the surface stated as x, y, z in three-dimensional coordinate system to the point given in the example is equal to, it is stated by little d, is equal to the square root, if you remember the formula, x minus 3 squared plus y minus 1 squared plus z plus 1 squared. Okay, and the constraint of this problem will be the equation of the sphere, because we want to find a point on the sphere such that we should maximize the function written here or minimize the function. So this is the constraint of the problem. Okay, therefore g of x, y, z will be the equation of the sphere. X squared plus y squared plus z squared is equal to 4. K is equal to 4. We have a function of 3 variables, you can see. So to get the maximum and minimum value of the distance function, so we use a simpler expression for this to get rid of the square root, to get easily the partial derivatives, you know. And since it is a positive function, when we take the square of this function, so we get the same points for maximum and minimum values of them. Okay, since d is a positive function, instead of d we take d square. In this case also we get the same points for the maximum and minimum value. Therefore, we instead of using the function d, we use d squared to get rid of the root function. So we have x minus 3 squared plus y minus 1 squared plus z plus 1 squared. The constraint is, as I said, the square of the equation of the sphere. So according to the method of Lagrange multipliers, we solve the equations for the variables x, y, z and lambda. And similarly, from the vector equality, namely we have the gradient vectors of the functions f and g, and we have the Lagrange multiplier here. The first one is corresponding to the first components of the gradient vectors, namely fx is equal to lambda times g of x, and similarly the second one is obtained from the second components of the gradient vectors satisfying this equality, and so on, and the last one will be the constraint. What is the partial derivative of this function with respect to x? So this is equal to 2 times x minus 3 times the derivative of inner function, which is equal to 1, you see, and the derivative of second term is 0. The derivative of last one is also equal to 0, and the derivative of the constraint is equal to 2 times x, you can see, times the Lagrange multipliers. Similarly, you can find the second and third equations taking the partial derivatives, and the last one is the constraint of the problem. So when we look at carefully the equations, in the first one you see just we have the variable x and lambda. When we look at the second equation, just we have the variable y and lambda, and from the third one we can say we have the variable z and lambda, and the last one is an equation for the variables x, y and z. So if you solve the first three equations for x, y and z, so we obtain these variables with respect to lambda, according to lambda, and writing them into the constraint, so we can find the value of lambda. Therefore, from the first one we write x minus 3 is actually equal to x times lambda. So from here we can write x times, writing this one to the left hand side, and minus 3 becomes 3 on the right hand side, you can see, and taking a parenthesis of x we get 1 minus lambda for the second multiplication, a second term in the multiplication. So from here x is equal to 3 over 1 minus lambda. Similarly, you can find y is equal to 1 over 1 minus lambda, z is equal to minus 1 over 1 minus lambda from the second and third one, and writing them into the constraint written here, which is the equation of the sphere, we get this one. And from here, after necessary computation, you can see lambda will be 1 plus square root of 11 over 2, or 1 minus square root of 11 over 2. These values of lambda then give the corresponding points x, y, z using the equations written here. Okay, we have two possibilities for lambda, therefore we have 2 points from the step 1 of the method of Lagrange method. So it is easy to see that f has a smaller value at the first of these points, and so the closest point is the first one. If you write this point in the definition of the distance function, you will get a value similar than the second one, and the farthest point therefore will be the second one. Okay, you can easily find. That's it. So now we consider two constraints for functions of 2 or 3 variables. Suppose now that we want to find the maximum and minimum values of a function f x, y, z subject to two constraints of the form g of x, y, z is equal to k and h of x, y, z is equal to c. How can we find the maximum and minimum value of a function when we have two conditions for the points? Okay, instead of functions of 3 variables, also you can write functions of 2 variables. So the first part of the method will be in this form, namely the gradient of f will be equal to lambda times the gradient of g, which is corresponding to the first constraint, plus we have another Lagrange multipliers, which is stated as mu times the gradient of h, which is corresponding to the second constraint. So for functions of 3 variables, actually we have 5 equations written here. The first 3 ones are obtained by using the equality written here, the vector equality. The first one is the equality for the first components. The second is the equality for the second components of this vector equality, and so on. Okay. So we have 5 unknowns: x, y, z, lambda, and mu. Therefore, sometimes we may not see easily the values of x, y, and z using these equations. For example, find the maximum value of the function f, which is a linear function, x plus 2y plus 3 times z, on the curve of intersection of the plane x minus y plus z is equal to 1 and the cylinder x squared plus y squared is equal to 1. So we have a cylinder here actually, and we cut this cylinder with a plane whose equation is given here. Can be like this, for example. We cut this cylinder with a plane, so we obtain a curve on the cylinder. So what is the maximum value of the function given in the example for all the points on this curve, which is the intersection of the cylinder and the plane? If you remember the section 12.6. Actually we will find an ellipse. So our aim is to find extreme values of f for all the points on this curve. So this is the intersection of the cylinder and the plane. So we have two conditions for all the points such that we want to find the maximum and minimum value of the given function. Okay. So therefore we have two constraints. G of x, y, z is corresponding to the equation of the plane, and the second constraint will be the equation of the cylinder, you see. So the Lagrange condition is the vector equality, which is obtained by using the gradient vectors of the functions. So we solve the equations, namely the first equality, is obtained by using the first components of the vector equality written here. The partial derivative of f with respect to x is equal to 1, you can see. Therefore the left hand side will be 1. What is the partial derivative of g with respect to x? So this is again 1, you see. Therefore we have 1 times lambda, which is the term written here, plus the last one is equal to mu times the partial derivative of h with respect to x is equal to 2x, you see. Similarly, the second one is obtained by taking the partial derivatives of the functions with respect to y, and the third one is also obtained by taking the partial derivatives of the functions with respect to z. Let's check. The partial derivative of f with respect to z is equal to 3. So the left hand side is equal to 3, you can see. Right hand side, the partial derivative of g with respect to z is equal to 1. So we have lambda times 1. And the partial derivative of the last one with respect to z is equal to 0. X and y are constant, you know. Mu times 0 is equal to 0. Just we have 3 is equal to lambda. So now we have already the value of lambda. This is very good. And the last two ones are constraints, you know. So putting lambda is equal to 3 in the equation written here, so we get 2x mu is equal to minus 2. So from here x is equal to minus 1 over mu. From the second one we get y is equal to 5 over 2 times mu. If write 3 for lambda, we get 5 for the left hand side, writing this one to the left hand side. So we get 5. So y will be 5 over 2 times mu. So writing them into the last equation, because we have an equation for the variables x and y. So we get 1 over mu squared plus 25 over 4 times mu squared is equal to 1. So from here we can write mu squared is equal to 29 over 4 after necessary computation. So mu is equal to plus or minus. We have two options for mu. Plus square root of 29 over 2 or minus square root of 29 over 2. So from these options we obtain x, the values of x in this form, the values of y in this form, and z is obtained from the equation written here. So it will be equal to 1 plus minus 7 over square root of 29. Therefore we have 2 points which are corresponding to the two possibilities of the Lagrange multipliers mu. The first one has the components minus 2 over square root of 29, 5 over square root of 29, and the last component is 1 plus 7 over square root of 29. And the second component, the second point, has the components minus plus 2 over square root of 29, and the second component will be minus 5 over square root of 29, and the last one is 1 minus 7 over square root of 29. Okay, so the corresponding values of f are, for the first point we have 3 plus square root of 29, and the value of f for the second point is 3 minus square root of 29. So therefore the maximum value of f on the given curve is 3 plus square root of 29 for the function f on the curve, which is the intersection of the plane and cylinder. Okay, thank you very much.